Okay, it's time to go. Okay, so we're working this week on getting more abstract concepts. We're kind of unleashing ourselves from the physical and attaching ourselves to the metaphysical, I guess. So we had a notion of a field that seemed really complicated at first, but fields are just sets that satisfy the properties of the real numbers. And since we mostly use just the reals and the complexes, there's not a whole lot of new stuff there except the name. Now, when it came to vector spaces, that was a much richer idea because it was kind of unsettling when matrices are vectors, scalars are vectors, vectors are vectors, whether they're row or column. Spaces of functions can be vectors. So that seems to be a much richer concept. And so writing down the axioms and being able to say, I prove something about a vector space and I handle all of those examples, that's a very powerful notion. And so vector spaces have two pieces. They have the set of vectors and the scalars over which you are working. And we'll hit that a little bit more today. We very carefully noticed that the addition sign is overloaded. We use addition for real numbers. But once you know what the addition of real numbers, you can then define what is the addition of matrices, for example. You take F to be the reals and you take N by M matrices. It's element-wise addition. That gives you a notion of addition in a larger set of matrices. And similarly with functions, when I evaluate a function at a point, you can think of it like an index. You know, you've got the ij entry here, the index, okay? Well, it's doing the same thing, and if you're doing MATLAB, normal MATLAB, not symbolic MATLAB, where you write your D here, maybe you called it capital T, is 0.01 to 100, and so you created 10,001 points, and then you said your function was sine of that. MATLAB just has a big vector of points, okay? So F of T is like an index. 0 is an overloaded thing because we have a 0 of the real numbers, a 0 of the complex numbers. What is a 0 function? Okay, let me ask a simpler question. What is a 0 matrix? 0 in every entry, right? So now, what is a 0 function? 0 for every value in every point in D, okay? So it's 0 everywhere. That's the 0 function. So when I add the 0 function to any other function, I get that same function back, okay? So 0 is an overloaded thing as well. Questions about vector spaces? We're cool? No, but we're not going to tell you, ha ha ha. Okay, we left off with this definition of a subspace. So we let XF be a vector space, Y a subset of X, so Y could be all of X. We don't do strict subsets or anything like that in 501. We say that the subset Y is a subspace of the vector space X, and you can write it just as X once the field is known, or you can be very, very pedantic and say X and its field F. If, when I take Y and I keep the field F, it is a vector space, and for a vector space you need rules of vector addition and scalar times vector multiplication. So Y is a subspace of X, you have to use the vector addition and scalar times vector multiplication that come from X. You can't make up a different set of rules. So you could have a different set of rules, But Y would not be a subset, a subspace of X. It'd be a subspace of something else or just a vector space in its own, but not a subspace of X. So when you're a subspace of X, you inherit the rules of addition from X. So to prove something is a subspace, in principle, we got to check all 10 axioms. We don't want to do that, so we're going to have a shortcut today. But remember, to prove something is not a subspace or not a field, you just need to fail one of the axioms, one of the 7 for a field, one of the 7 for a subspace. So always, always, always make sure the 0 vector is in your set. That's the easiest thing to check, okay? Remember, the 0 vector, not the 0 number. So the 0 function, the 0 matrix, the 0 vector. Okay, ready to start for today? Okay, let's do it. So let's have, let's see, proposition. The following are equivalent for a vector space XF and Y contained in X a subset. Okay. The following, let me capitalize that one, are equivalent. We'll use TFAE quite a bit. Okay, so I'm going to give a bunch of different things, and they're all going to be ways to check. Okay. Y is a subspace of X. Okay, so that's the property we would like to check. For every vectors v1 and v2 in Y, their sum is also in Y. Okay. Take an arbitrary pair of vectors, their sum is in Y. Orally, one says Y is closed under vector addition. Okay. Y is closed under vector addition. And for every element of the field and for every vector in Y, alpha times V is also in Y. Okay, we're going to give some more. So one says Y is closed under scalar times vector multiplication. Okay. So if you do this and you get something that's not in Y, it's not a subspace. So here you're checking 10 things. Here you're checking 2 things. We've won by 8, okay? So this is a win. There's many ways of writing this condition down. So you'll see in books. So we'll just do many of them here. You can say for every alpha in the field and for every pair of vectors in Y, the sum alpha times V1 plus, not alpha, just V2 is in Y. Okay, so here I'm checking in principle only one thing. We'll talk about that. And then the last way you'll see this written down is for every pair of coefficients in the field, and for every pair of vectors in Y, alpha 1 V1 plus alpha 2 V2 is in Y. Okay? So that's the proposition. Okay, we're not going to do the proof except a little bit orally here. You can do the proof at home. But to prove D implies C, that's simple. You choose alpha 2 equals 1. Okay, then D implies C. Bingo. C implies B. Well, if you take alpha equals 1, then you get it closed under vector addition. And if you take V2 equals 0, it's closed under scalar times vector multiplication. Okay, so C implies B. B implies C, you check all 10 axioms. So this one condition will get you all of the 10 axioms satisfied. That's the hard one. And then A implies B, well, it's a subspace, so it satisfies these. So you just do it in a circle. So I don't expect anyone will actually do it, okay? Don't worry, but that's exactly how you'd go about doing it. Questions on why this is useful? We're going to do some examples, but it takes the 10 conditions down to either 1 or 2, and it's up to you. Whether it's easier to check vector addition separately and scalar times vector multiplication, or you can check them together, or you can just use one scalar. It's your call. They're all equivalent, TFAE. So that's what it means. This thing implies this thing, implies this thing, implies this thing, implies this thing. If and only if and only if and only if. Okay. I'm getting the I am not totally thrilled look. Okay. Let's just do some examples. 1. XF is equal to R2 and R. Y is, everything that looks like beta, 2 beta, and you'll see why I want to do this, beta in R. So just want to go through once, checking the conditions. We're going to apply the proposition. So is this set a subspace of R2? So what you would check typically is, let's check if it's closed under vector addition. So we'll put a beta 1 and a 2 beta 1. Take another arbitrary point in Y. So here's our V1, here's our V2. I don't know, man, let's do it. So this is now beta 1 plus beta 2, and I'll leave out one step and just write this as 2 times beta 1 plus beta 2. So that's in Y. Closed under vector addition. We're going to check next. Closed under scalar times vector multiplication. Everybody's, they've already done it, I can tell, but let's just do it. Okay, so we let alpha be in the reals, and we do alpha times an arbitrary vector. Here's a vector V. Whoops. And by the way multiplication works, we'll take advantage that it doesn't matter in what order we do these multiplications. That's in Y. Okay, so closed under vector addition, closed under scalar times vector multiplication. It is a subspace. Too simple? Yeah, so when we have here, you can do A, check all 10 axioms, your choice. Probably not the one you do. Here, you can do this one. So then you do vector addition and scalar times vector multiplication. You could have said, this one is so easy, it's easy for me to go alpha times beta 1, 2 beta 1, and then beta 2, 2 beta 2, and add it and show it's in here. Then I just have that one step. Or I take two scalars and two vectors, so you do any one of these. That's what you have to do. Yep, that was the question. Question?
So in this example, it's obvious that there's zero vector, but you just get to like state that, you know, if you make beta equal to 0, then you have the zero vector in the subspace. Is that necessary?
Do you have to state that? Well, if I take, this is for every alpha, so if I take the 0 element of the field, and it's closed under scalar times vector multiplication, then the 0 vector is in here because the 0 scalar times any vector is the 0 vector. So it's automatic once you check this. But we're going to do an example where instead of doing all this, we just note immediately that 0's not in there, we're done. One non-axiom, we're done. One axiom not being satisfied. Other questions about strategy? No? Yes? Excuse me?
Usually it's just factorization.
Factorization. Well, I don't know what factorization would mean, but it means whatever properties define this set, you need to show that these operations preserve it. So I could have functions, and I have functions whose derivative is 0. Okay, that's my subset. Is that a subspace? If I add two functions whose derivative is 0, is it once again a function whose derivative is 0? Yes. If I take a function whose derivative is 0 and I multiply it by 17, is its derivative 0? So it's closed under vector addition and scalar times vector multiplication. So there's no factorization. I'm checking the properties. Yeah, so that's how you do it. You check that it's an element of whatever conditions define Y. 2, I'll keep my field as the reals, and I'll take my vector space as F takes R to R. Okay, so we know this is a vector space. I'm going to define Y to be definition equal to this set I'm going to call P of T. And it's going to be all polynomials in T with real coefficients. Okay, so everybody happy with polynomials being functions? Cool, okay. Now, is this a subspace? Well, if I add two polynomials, do I get a polynomial? Yeah. If I take a polynomial and I multiply it by a scalar, do I get another polynomial? Yes. Okay, so is a subspace by checking the proposition, okay? Here's the other example I just said. Y tilde by definition equal to set of O F takes R to R, F differentiable, and d by dt of F identically 0. Okay? So this is a subset of X. So that's also a subspace. Because if F has a zero derivative and G has a zero derivative, their sum has a zero derivative. If F has a zero derivative, then 3 times F has a zero derivative. This means everywhere, okay? It's the zero function. D by dt applies to F is 0. So also a subspace. So there's lots of examples like that. And then a non-example. Non-example, let's see, what do I have here? Oh yeah, okay. I'll define my vector space to be, once again, R2 and R, just to keep it that simple. Then Y will be things that look like this. Beta, 2 beta, plus 1, 0, such that beta is a real number. Okay, so I've got similar to the example we already worked, except I added an offset to it. Is that a subspace? Okay, we have 1 vote for not.
Said non-example.
Yes! I love it, I love it, I love it, yes. Okay, 0 is not an element of Y, okay? So, not a subspace. So that's the easiest thing to check. So I can't write 0 as some constant plus 1, 0, because if I put the constant here, it's 0, then this is 0, and I get a 1. So 0 is not in there. And note, 0 is 0, 0 in this case. Okay. So, moving on to now one of the key concepts, linear combinations and linear independence. If we get this, today's a success no matter what else happens, okay? So we get this, in the abstract, life is really, really good. So for the following, I'm going to let XF be a vector space. Okay, so now when I write down a definition, I'm not going to repeat let XF be a vector space every time. Okay, so it's going to be definitions about this set. Okay. Definition 1. A linear combination is any finite sum of the form alpha 1 v1 plus alpha 2 v2 plus alpha n vn. Whoops, hit my little erase thing here, where n is bigger than or equal to 1, alpha i's are in the field, vi's are in X, I greater than or equal to 1, less than or equal to n. Okay. Okay, this does not mean v squared, okay? I will usually use the subscripts for if this is a real vector and it has components v sub 1, v sub 2, v sub 3, v sub 4. So this is not like x1, x squared, x to power n, okay? Those are just elements of x. The superscripts are not powers, okay? So this is linear. There's no cosines or squares or anything. But the key thing is finite here. Okay. So you guys are used to looking at Taylor expansions, for example. So you like infinite sums, okay? This is not a linear combination. So this is absolutely the hardest part of this. It's not that hard, but it's really, really important. You cannot have infinite sums. That is not an allowable linear combination. So let me explain why. Okay, but it's a definition, and it says it has to be finite, so this fails, okay? It fails, but fails the definition. But why? What does that sum mean, okay? Sum I equals 1 to infinity alpha I vi really means limit n goes to infinity sum I equals 1 to n alpha I vi, okay? Right? That's what this notation actually means. It means a limit. Now, what does a limit mean? Well, in the end, it has to be getting close to something, right? Okay? So, what does it mean that two vectors are close? You know, if you're in R2, you might say, I use the Euclidean norm and I measure distance like that, okay? Now, I'm in matrices. What does it mean that a bunch of matrices are close? What does it mean that a bunch of functions are close? Okay? So in a vector space, without additional structure, there is no way to measure what close means. So things are having a limit, okay? So without additional structure, we cannot define what it means to converge to something. i.e., that is, has a limit, okay? Okay, so this is the only important part of that definition is the finiteness. So make little notes on that one. Questions? So it's just that way, okay? So for me, when I was learning it, it didn't bother me. I just said, it's that way, fine. Anybody can make any definition they want, whether it's motivated or not, okay? Some of you don't like that, so I'm just giving you the motivation, and we will come back to this, because later in the course, we will understand exactly what it means that an infinite sequence converges to something. We will be careful about that later in the course, but we need more structure. Okay. Definition. I'm going to do one thing first before the definition. I'm going to do a mindset thing here. So I'm going to cheat, erase. Okay, I'm going to hopefully help you, but maybe I'll hurt you, okay? Let A be an n by n real matrix. Okay? Let X be some point in Rn. Fact, A is invertible if and only if the only solution to AX equals 0 is X equals 0, okay? So I'm just hoping everyone in here has had some experience with matrices and conditions for solvability of equations and having unique answers and stuff like that, okay? If not, go to Wikipedia, look it up. So let's just take this as a fact. Now, why am I wanting this as the mindset? Let's write A as a partitioned matrix, just like we did in homework. Okay. And let's write X as x1, x2, xn in terms of its components. Exercise. So I hope everyone will do this at home. Okay? A times x can be written as x1 times a1 plus x2 times a2 plus xn times an. So what are these called? The columns of A, right? What does this look like? Since x1 is a real number, x2 is a real number, this is a linear combination of the columns of A. So just use what you know about matrix times vector multiplication, and you'll end up with A1 times x1. But it's a scalar. You could move it to the other side. Okay? You'll end up with A2 times x2 and an times xn. So just move them like this. That's the exercise. So What are you asserting when AX equals 0 has only the trivial solution, x equals 0? Okay? You're asserting that when you look at this linear combination of vectors, the columns of A, the only solution that makes these vectors add up to 0 is the trivial solution, x equals 0. That's what you are asserting, even though you weren't thinking about it that way. This is just mindset. I'm going to make a definition, and then I think you'll see the connection. Okay, that's mindset. Definition. Definition. A finite set of vectors v1 to vk, and they are elements of x, is linearly dependent if there exist scalars, so alpha 1, alpha k in F, I am such a hoser, okay? Mixing up your notes. Not all 0. Okay, there exist scalars, not such that not every one of them is 0. Such that when I form the linear combination alpha 1 v1, alpha 2 v2, alpha k vk, I get the 0 vector. So the notion of linear dependence is finding non-trivial solutions to a linear combination that adds up to the 0 vector. Let me complete the definition. Otherwise, v1 to vk is linearly independent. Okay, and let's write out carefully what the otherwise means. Means the only solution alpha 1 v1 plus alpha 2 v2 plus alpha k vk equals 0 is the trivial solution alpha 1 equals alpha 2 equals ... equals alpha k equals 0. Okay. Everybody still writing? Not writing? Okay, so we're used to talking about uniqueness of solutions of equations or looking at the condition AX equals 0 and having only a trivial solution as being something important to us. what it was really doing is asserting that the columns of A are linearly independent, okay? That's what we were always doing. And so this condition is asserting, I write down the linear combinations of the columns of A, I try to form the zero vector. The only way I can do it is xn equals 0, xn minus 1, x2, x1, all 0. That's independent. And so a general set of vectors, whether they are functions, matrices, things in Rn, anything else that I can't even possibly imagine right now, we have the same concept for linear independence and dependence. Independent, the only solution to the equation is 0. Dependent, there is at least one solution with one of the alphas non-zero. Could be 2, could be 3. Okay, all you need is just one non-trivial solution. So that's independence, only the trivial solution. Dependence, any non-zero solution. That's it. I mean, that is absolutely fundamental in this defining vector spaces, notion linear independence. Questions? We'll do examples, but see where the concept comes from AX equals 0, okay? Just extending that. And then we'll do the last definition and we'll do examples around it. Definition. An arbitrary set of vectors is linearly independent if every finite subset of vectors is linearly independent. Okay, so this one is totally abstract, but we'll use it. But the first thing I want to do is really illustrate how you check for independence and dependence of vectors.
So,
Yep.
this is excluded itself, otherwise can never be satisfied. Like, the subset can also be the set itself.
Yeah, that's fine. But it's not finite, maybe. Okay? Yeah, we're going to do an example where the set has an infinite number of elements, and we will check that they are linearly independent. There's no finite subset that is dependent. Okay? Every finite subset is independent. Why do we have to go to the finite thing? It's because we can't write down this equation, okay? So we have to reduce it to the finite case. We look at every possible n. We don't do the limit, but we look at every single possible n and form all those combinations, and we check that the only way you can get zeros if all the coefficients are 0, okay? That sounds really hard, okay? Really, really, really hard, but we'll do it. Other questions? Okay, so that's the notion of independence, and it's really tied to uniqueness of solutions of equations and many things like that. So, examples. How do you check this? How do you do this? So, we'll take it equal to R2 and R. I'll let V1 equal to 1, 1. And I'm going to make it easy on myself and you. V2 is 4, 0. Is the set V1, V2 linearly independent. Okay. All of the solutions look like this. Let alpha 1, alpha 2 in R be arbitrary. So you take arbitrary elements of your field. We're doing the real numbers. So here's my F. I form the linear combination and I set it equal to the 0 vector. And I look, what type of solutions do I get in terms of my unknowns, which are the alpha 1 and alpha 2. Okay? So this equals 0, if and only if. So I need to do alpha 1, 1, 1, plus alpha 2, and you can see that I'm kind of cheating, making the example too easy, okay, is equal to 0, 0. Okay, and so that's if and only if I have alpha 1 plus 4 alpha 2, alpha 1, it looks like a 6, okay? It's not, it's a 0. Not any better. Yeah, I know. Okay, so now I have 2 equations and 2 unknowns. And I made it triangular and simple. So alpha 1 is 0, and once I have alpha 1 is 0, I get alpha 2 is 0. So it's trivially the alpha 1 equals alpha 2 equals 0 is the only solution. Okay, so conclusion, linearly independent. Too easy? No? Questions? Let's do another example. And I've got it written out, so just write in your notes. Okay. See example. Okay, and I'll insert this into the notes and you can copy it into yours. It's just I didn't want us to spend time copying it down because it's the same thing, but just on a little bit bigger scale. So I'm still keeping my field R, I'm still keeping my number of vectors 2, so I don't have too many equations to write down. But now the vector space is 2 by 3 matrices. There's A1 and there's A2, and I ask myself, are these vectors independent? So I do the same thing. I write down an arbitrary linear combination and I ask myself, how can I form the 0 vector? Okay. So I write down what is the 0 vector. I write down the linear combination. And so I get alpha 1 plus 4 alpha 2 in the first entry. I get 0 times alpha 1 plus alpha 2, etc. So I just use the matrices and I write down these and I set it equal to the 0 vector. So this is where people mess up. They forget what is the 0 vector when they're working with the vector space. So I have 6 equations now in 2 unknowns. If I wanted to be really mean to you, I would give you 5 matrices, and you'd have 5 equations and 6 unknowns. 6 equations and 5 unknowns, okay? It would be horrible. You wouldn't like me, but it would be the same thing. You have all of these equations, and the number of unknowns is the number of vectors. So you have all of these equations have to be satisfied. Well, you know, I cheated and put 0 in some key places, so I get alpha 1 equals 0, and I get alpha 2 equals 0, so they're independent, okay? But I could have put no zeros in there, and then you have to go through here, and you pick 2 of them and see if you get a solution. Maybe there's a non-trivial solution there, and I try a different 2 and there's not. All of them have to be satisfied, all 6. So it's hard for 2 unknowns to satisfy 6 things, but they can. If I make A2 equal to 3 times A1, then they are linearly dependent. See how the examples go? Okay. So this is a vector space that has 6 elements. Let's do one that has an infinite number of elements now. It's got to be more fun, right? Let's see. Is this what we're doing? Yeah. Okay. So you've already got that. I'll insert that page here in the notes. They will continue beautifully, etc. So here's another example. Okay. Remember, this is the set of all polynomials with real coefficients. So that's my x and my f, just to be clear. I'm going to take a set which consists of the monomials, 1, t. Now this superscript does mean power, okay? Equals all monomials, so all powers. And my claim is that S is a linearly independent set. Okay, the monomials are linearly independent. I'm going to use a new technique. It's called lazy induction. That doesn't really exist, okay? It means I'm going to cheat a little bit, and then I'm going to paste in the correct proof, which has every single step, okay? I'm just going to give you all of the main ideas. So this is how I would scribble down a proof on a sheet of paper, and then I would type it up for my journal much more formally, okay? But these are all the ideas that I need to write it up formally. So I'm giving you the lazy sketch, okay? So they're also called a sketch, okay? So it's also called a sketch of the proof. So please don't quote me in some class and saying, I use Professor Grizzle's lazy induction method, okay? I beg you. I do have some pride. Not much, but I do have some pride, okay? Okay, so let's take an arbitrary linear combination of elements of S, but finite. Take an arbitrary but finite combination of elements of S. So I will define that to be a polynomial P of t, and for reasons that don't surprise you at all, I'm going to write it like this, okay? If you want to put alphas here, go for it. So these are just real numbers, and these are vectors. Whoops, that should be 1. Wait a minute, it is 1. Oh, that's a plus sign. No wonder I couldn't even tell what was going on. Yeah, I know. I wish I could say I did that for comedic effect, but it's not true, okay? Okay, so here's arbitrary, because K is arbitrary, okay? So fine. Some of these are 0 because I only wanted to do 1t, skip t squared and go to t to the 7th. I really don't care. Okay, so to show P of t equals the 0 vector if and only if A0 equals A1 equals dot 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 equals AK equals 0. Okay? That's the definition of linear independence. This has to be the 0 vector. Okay, now, so what does it mean for a polynomial to be the 0 polynomial? It's 0 for every value of its argument t, okay? So this is absolutely crucial. What is the 0 vector? P of t is the 0 vector if and only if for every point t in R, let me call that t0, so you think about that as a fixed value. I get the 0 number in R, okay? So this is t, a general argument. This is now a fixed value in its domain. I search over all of them. When I evaluate the polynomial, I should get 0. It's identically 0. It's identically 0. Okay. So there's my polynomial. Now, what if I happen to take t0 equals 0? What do I learn about my coefficients? I get A0 is 0, right? So I just observe. Yeah, that's what I'm going to do. Observe. P at 0 equals 0 if and only if A0 equals 0. Okay, so I didn't have to search over all possible t0s. I got this. Okay. Now, this one is kind of the trick here. Okay, so I'm checking if p is identically 0. That implies that its derivative has to be identically 0 as well. Okay? So remember, I set it equal to the 0 vector, so it's the 0 function. It's 0 everywhere. The 0 function is differentiable, and its derivative is 0. There's no problem there. Well, d by dt of P of t is A1 plus 2A2t plus dot 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 k times t to the k minus 1. So if this is equal to the 0 vector, okay, I now evaluate it at t0 equals 0, and I get a1 equals 0. So conclusion. Oh, I missed my, I put it here, k times ak. Is that better? Yeah. Any other big mistakes? No. Okay, so conclusion, 0 equals d by dt p of t implies p dot at 0 equals 0, which implies a1 equals 0. So p dot d by dt, okay? So the derivative of p, I get a1, and then continue by induction. Okay, so I'm going to paste in a, well, let you get this far. Ask questions. I'm going to paste in the correct induction proofs. It's a little more careful. It's not quite as lazy, but I think you see how I continue to the second, and then by induction I get all the way. So it's fine. Boring? Yes, question?
I think I might be mixing something up. So you said that the definition of linear combination is finite. Is that?
Mm-hmm.
So this monomials you have, it's not finite.
Correct. 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 But an infinite set is linearly independent if every possible finite set is linearly independent. So you give me a finite set. How many elements can it have in it? 10 billion, whatever, okay? What's the degree of the highest polynomial in there? 9 trillion, okay? So I take, whoops. My k is now 9 trillion. I've taken an arbitrary subset of there, okay? And I've written down a linear combination of that subset. So that's how I handle that. So I go for every possible k, and I get every possible subset of that. Other question? Question?
So instead of the differentiation, can we take the common out? That doesn't happen. So from the expression, once we prove a naught is equals to 3,
Mm-hmm.
we take the t common,
Mm-hmm.
the main expression, and then we can prove a1 is equals to 3.
Well, yeah, so if you take out a0, but now if you plug in 0, all of these things are 0, so you got to do something. You can plug in 1 now and get a set of equations. You can plug in 2, get another set of equations. You can write down a matrix. You can prove that that matrix is invertible. That's the harder way. Okay? You can take, instead of doing 1, 2, 3, 4, you can do pi, e, square root of 11. You just do a whole bunch of different numbers. You'll generate a matrix. You prove that that matrix is invertible. It's multiplying this vector. That vector has to be 0 if the equation is 0. There's many ways to do it. Cool. Okay, so let me, whoops, I don't want to do that. I'm going to paste in a correct proof, so. Bingo. Images. Today. Monomials linearly independent. Open. No, it's not bad. Okay, so you have a correct proof by induction in there, which sets up a base case. It sets up a hypothesis on the integers. It does the base case, it does the induction step, and it does everything for you. Okay, so it follows the same ideas by doing differentiation. The derivative of 0 is 0. And so the second derivative of 0 is 0. The third derivative of 0 is 0. The fourth derivative and the kth derivative, etc. So. happy so far? Question?
So for a trivial solution, you're saying that there's only one solution, that all one to all A is 0, right?
Yes, that's what I mean. So let's go back and just make sure the vocabulary is cool there. Yeah. So 0, 0, 0, 0 is always a solution. The question is there another one? Ax equals 0, x equals 0 is always a solution to that equation, okay? If there's another solution, ax equals to 0 with x not equal to 0, we know a is not invertible, okay? The same thing here. If there's another solution besides the trivial one, it's trivial because it's always true, 0 is the solution, then the vectors are dependent. But if the only solution is the trivial solution, 0, 0, 0, 0, 0, then it's independent.
Well, then there's another solution that where some or some alpha k is not equal to 0, then if you get 0, then the scale of multiplication of the solution is also the solution. So would there be like either one solution or a solution?
Sure.
So if I find a solution that's only one solution, then can I effectively call that a 0 solution?
Okay, the question is, just so everybody's getting it, suppose you find minus 1, 4, 11, blah, blah, blah equals 0, and you prove that there is no other solution than that. Theorem, you have made a mistake.
Yeah, how's that possible?
It's impossible, okay?
Multiply 0 by it, and get a
Yeah, so there's always 0 is always a solution. So you can't have 11, 3, 7 being the unique solution to the equation. It's not possible. Okay, so you're just checking, is 0 a solution? That's always true, but if there's another solution, you're done. You don't have to find all of them, you just find one. So it's just like showing not a field, you violate one axiom, you're not a field. You're an axiom, you have to solve all of them. To prove dependence, you find one set of coefficients, not all 0, they're dependent. To prove independence, you have to check all possible coefficients and show that they're not a solution, only the 0 is the unique solution. Question?
When we assume that derivative of 0 is 0 by induction, are we assuming that we are strictly dealing with polynomials? Like sine of 0 can be 0, but when we take the derivative, the cos of 0.
Well, in that case, we're checking that the derivative of we know the derivative of a polynomial is another polynomial. Yeah. I guess I'm not proving everything. Yes, I should have differentiated, but I'm differentiating 0, and I know I get 0 and 0's in the set. Then I just calculate the derivative. And I use the standard rules of calculus. So this is how proof goes. You get to use the standard rules of things that are theorems and derivative of polynomials. Take the powers down, put your coefficient in there. Life is good. Okay, so here's the next important part. So we've got that, is definition. Let S be a subset of X. And since it's been so long since we've stated it, XF, a vector space. The span of S denoted span of S, or simply span S. Whoops, what happened here? Is the set of all possible linear combinations of S. Okay, I'm going to write it down, but this is it. You build all linear combinations of S. That's called its span. So what does that look like? Span of S is equal to all the vectors in the original subspace for which there exists some integer, some natural number k, bigger than or equal to 1, coefficients in the field, vectors v1 to vk, an element of S, such that x equals alpha 1 v1 dot 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 alpha k vk. Okay, so these are linear combinations. Why is that all possible linear combinations? Because I'm searching over all possible indices in numbers k, all possible coefficients in the field, all possible vectors in S, and forming the linear combination. Okay, so that's the span. Question. Take two vectors now that are in the span and add them together. So I take one linear combination, I add it to another linear combination. What do I get? Another linear combination. Take a vector in S and multiply it times a scalar. So I have a linear combination, I multiply it times a scalar. What do I get? Another linear combination. So what do I know about span of S? It's a subspace. It's closed under vector addition and scalar times vector multiplication. Okay? So that's why span is so important. Span of S is always a subspace of X. It's closed under vector addition and scalar times vector multiplication. Okay, so linear combinations are finite. Now I'm doing all possible linear combinations of elements of S, and that's the span. Examples. F equals the reals. X equals all functions from R to R. S equals the monomials. What do I get when I take the span of the set of monomials? I get all possible polynomials in T. They're finite. Okay? Okay. Question. Is e to the t an element of the span of S? Okay. You guys know the exponential function? You've seen that once, twice in your life. Yeah. His friend is the logarithm. Okay. So is e to the t in the span? Can I write it as a finite combination of monomials? No. Okay. So the answer is no. This is super important, okay? Only linear combinations. And it's not like e to the t is a nonlinear combination. The problem is it's an infinite thing, and you have to know about convergence and calculus to define e to the t, okay? So that's the... So this means finite sums. Okay. I had my f equals r to the 2 by 3. And then I don't know what I had, 1, 0, 2, 0, 3, 4, 5, 0. Whoops. 2 by 3, and I've got 4 entries. So what's easier to change? This number. And 1, 1, 1, 5, okay. Okay, so you would get all 2 by 4 matrices that you can write as an alpha 1 in the upper corner, an alpha 2, an alpha 1, an alpha 1, let's see, an alpha 1, a 2 alpha 1, a 3 alpha 1, a 5 alpha 1, plus a 4 alpha 2, etc. All of those matrices. Okay. Okay, we are 2 minutes till the end, so we stop here. Okay, so bingo.